Hi everyone, my name is Chen, and I'm gonna give lessons, an introduction about famous data structure or so-called algorithm. His name is KD tree, and maybe we can start it from the GitHub event. So here, if you haven't had this following things, I recommend you to install as fast as possible. And today's goal is to try to make our versions about the fast searching algorithm. So if you're familiar with Launchbox, I believe this create RT3 components and this concept. This will be the closest RT3 closest point. So my goal of today is to replicate this fast searching algorithm, and by creating ourselves with different approach. So maybe you know there's a R3, final comment R3. Oh, sorry. There's a class called R3 here. Some of the fast searching algorithms implement these special searching structures to speed up the searching speed. And today I'm gonna introduction the other ones, not like default R3. I create the other one so-called KD tree. So let's take a look about my GitHub page. Oh yeah, I have a link here, so you can see the definition about R3 if you want to learn more. And some other special trees called quad trees is also interesting and recommend to learn. And today we'll focus on KD tree. And what is a KD tree? K means you can put any numbers inside K. So there, for example, there will be a 1D tree or 2D tree. Follow along to a KD tree. But since the Rhino is a 3D graph software, so today we're going to have a 3D tree. So far, everybody can catch up. Okay. So why we have to have a tree, and for maybe someone not familiar with tree sense in computer science, tree is a abstract data type, and tree maybe you heard it before, but I list some of the important properties about a tree. So this sentence I copy paste from a wiki. We can all watch together. So first we know it's an abstract data type, and it's like a hierarchical tree structures, and has a root value, and also has subtree, and also tree, also children's, and a parent node. So I list some ideas about a tree here, and we can learn one by one. So here I think the important of a tree is, for one, is no circle. There is no cycle. What is a cycle? Cycle means that like a graph here, if you can go back to one root. For example, if you go down, and for a definition about a proper tree, you cannot go back to the origin. Like for example here is, once you leave A, you cannot go back to A, follow the other paths. Is anyone clear here so far? So if we try to understand the hierarchical means, it's basically like the graph here. So let's say in your family you have your child and you are their parents, and also you have your own parents, or maybe you have your grandparents. So the level is very clear. But if once you have the cycle here, the level will get confused. Why will make this confused? For example, this one is not a tree. This one identify the graph information about the two inside this this picture, but you didn't know the hierarchy. You didn't know who is on the topest about this relationship. So the important about a tree structure is you will always know who is the, for say this, who is the grandparent about one big family. Can everybody know this idea so far? So one thing I think very important here is to construct a tree, we should guarantee there's no cycle inside this data structure. And secondly, we have node and so-called vertex inside a tree idea. For example, here, for each person, I for example, is a grandparents, parents, or you, is a people. So now this one is a node, and node contains the information about a person. And the relationship between you and your father will identify your father will be your parent node and you will be your father's child node. So the relationship is upside down for like you can say the one maybe here the girl will be this man's daughter, and this man will be this man's son, and this girl will be and this man will be this girl's father. So the relationship will maintain very clearly. And the other is a tree, but this seems obvious, but it will get very confused follow very soon. So if we follow the idea about a family, you can see here maybe is this identify a very big, very large family, have a lot of people. But if you split it into very small pieces, this one can be its own family. So this idea about the family inside a big family is so-called a subtree. So we have a big tree, we have a small tree inside a tree, is so-called subtree. So follow this logic, it will be a lot of subtree inside a very big tree. Okay, so far, does anybody have any questions? So since we have a lot of these hierarchy level properties, we can do something recursively inside our code. So one thing to implement a tree structure is to use recursive function. And a recursive function is a function whose code itself inside its definition. We will see later on. But now I'm going to give an explanation about what is a node. So as I said, for the previous example, a node is a person. So the information contents will be a person. But for this case, we only want to know the point, which is the closest between a lot of points. So the information will be stored as a point 3D data type. But if you want, you can use this algorithm to do something like, you don't need to have to, what I say is you can do something like family member. By doing this, you can construct another tree which node contains different information. So it's a thinking about, basically it's a thought, and how you transfer your problem into a solution depends on how you think about the questions. And one thing interesting in here is, inside our class node, we also have these two member, and this two member is also a node class. So if you think about, I named it left and right because each node has two nodes connected. You see binary tree. So KD tree is one of a binary tree. So what is a binary tree? Binary trees guarantee a single node have two child nodes at most. So if you see here, as a one node, I will have a left node, and also I will have a right node. And in this sense, the left node and right node here actually means address, a pointer point to this information. But follow this logic, you can see this node also contains the pointers point to the other two. So if you grab from the root, grab from the topmost node and pull it up, all of the information will visually connected to each other. All of them have relationship. So how can we, starting from one node and traverse and go to the other node, is something we were going to do. And the class here is very clear and simple. The constructor of this class is, if we given a point, we will store this information inside our node. So far is the definition about is the fundamental stuff I'm trying to construct a tree. Okay. So, well, maybe I have talked about this bit, but you can, if you have any problem, you can try to catch up from the description here or the link I copy paste here. There's some terminologies about a tree. You can see that, for example, there's a height, depth, or level of a tree, and it represents a different name about the property of construct one single tree. Okay. So far, I give a very brief introduction about a tree inside a computer science sense. Maybe some of the members here haven't used a tree before. Might think this is a big topic, but actually it's very fundamental if in the computer science field, but it's very hard to learn for the first time for me as well. So far, any problem?
All good.
So I believe many of the members attend to my lesson of this time. Also attend to Kawasan's lesson about the fast searching algorithms, a lot of points, and I believe he used this point 3D list to find the closest point, like this one, closest I index. So this class basically, I believe, it implements one of the fast searching algorithms. And so why I saw this binary search things, I can confirm this class also construct a binary tree before you do the fast searching algorithm. Okay, so that's one thing I want to mention is, and also maybe you were wondering why we have to have a tree to speed up the searching process. Is that if you think about the way we used to find the closest tree very naive way, maybe let me try to open the. So people see my GitHub can download the file here, and I'm really bad at organizing my file, so let's do it again. Oh, where is it? So I just put it here. Okay, so if you open my repository, I have this closest point .grasshopper. You can see together. So here. So here is one attempting experiment. I try to confirm that my algorithm is faster. So we can take a look one by one by get rid of these things. And there's too many points. So, oh, yeah. My drop code. And so while we're waiting my computer, we can all think about naive way of finding the closest point inside the first things come to mind will always be a for loop. So you may try to do a for loop and for loop inside something, and to get the distance, maybe distance of 2 points, point A and point B, and storing distance, maybe we can say as a double, and compare here to distance or distance to something max. If it's bigger, then override it. If it's bigger, then override it. Or something like this. This is very intuitive way of thinking about how we find the closest point. Even if I disable my canvas is also very good. I want to disable it. Okay, so far it's great. Maybe you can start it from 1000, or maybe it's slow. Okay. Here we can do top 3D and do like 100 points. And we can give this one. Okay. And also we can have a certain point. Okay. So the thing I do is we have this populate 3D, and among these 100 points, I want to find the points closest to the points I assign. So let's set 1 point here. So this according to the list calculation is search up to this one is the closest, which very obvious if we see in person. But what is inside here? So inside here is very intuitive. Basically, everyone will come to their mind at first place. Is you have this distance property, distance number, and you compare to the distance about each. You just connect them and compare to, and select the closest one. But we actually implement one for loop, and this loop's length, if we have 1,100 points, then we have to run 100 times. So it will get worse if we have a lot of points. We basically have to run a lot of times. So let's say the searching process takes n times so far. But why to construct a tree will be faster is that compared to a tree, you will go let the searching process go to log n time. so far. But why is log n? If we think about this diagram, you see, we're starting from a node, and maybe this one, 21, will be the closest point. How we should go to 21? We'll go down here, go down here, go down here, and then find a 21. But this structure contains a lot of points. How and why we don't need to traverse, why we don't need to go to test each point to find the one we needed. Because we can understand in this node, we didn't need to go to the left part, we just get rid of it and go down to the right part. So here I say the tree only takes you log n time. What is this log n comes from? You think about it's a binary tree, so every node in this level will be something about 2 factor. So you see this one is 2 to 0. This one is 2 to 1 equal to 1 equal to 2. It's 2 to 2 to 2. Can everybody knows me? I'm trying to say is this things. So I because my English is not that good, so but I know a saying about this expression is 2 to 2. 2 has the factor of 2. Okay, so what I say is we have 2 to 0 as node, 2 to 1 as the binary tree. Maybe we can do something like this. Okay, so we keep focus on this one, and 2 to 0 is 1. This one. 2 to 1 is this one. 2 to 2 is this 4, 3, 4, 5, 6. So I'm trying to explain this, and for like if we have 6 layer, we have 6 level, we can contain 64 points. So for like the example here, we have this point, this node here. How many tasks, how many calculations do we need? Like 1, 2, 3, 4. And why we have these 4 numbers as the times we travel is because it's the same as the node here level, and also the same as the number of this one, 4. So in this layer, we have 16 nodes. So the opposite about exponential will be the log. So we actually contain exponential things. We contain things exponentially, but while we searching, we kind of press the information so that the searching process we only have to do in the log sense. So far, any problem? So I think this one is very difficult to understand, but since I'm bad in Japanese and I'm not very good at English, and maybe I make this explanation even worse. But so far, I just want to know if everyone follow this idea or have any problem here.
I think I'm fine.
of the other members. So far, I'm trying to say, as a tree structure, it contains things exponentially. We have a lot of points here. But while we're searching, we can just do it in log time. And these logs make the searching process faster than we do in the end time. Okay, and let's go back to my file here and reading everything. So here I compare this one is not if search, and this one closest point. I think this one is also the points 3D list have a tree structure, so it's faster. And this one is I try to use C# script to do points 3D close. I just code it inside. And this one interesting is from the launchbox, we have this component to create an R tree and also use this R tree structure to search the search point with the benefit of this structure. So these four things might be as fast as like very close to each other. But since I think there's no one bring KD trees to KD tree implementation into Rhino publicly, so I think it's good to if we can do together. And so starting from now, I'm formally going to explain what is a KD tree and how we implement it. So if you see the file about this explanation demo I created, you can open it. And here, I think it's hard to visualize in 3D. So I try to visualize in 2D first. And once you get that sense, we can just think about 3D and do 3D tree. So this example is very interesting. And first I should explain what is this point about. Like think about the red point. For instance, other point cloud we need to search. We need to construct a tree structure, and this one will be the point. Okay, let me try to explain this way. The blue one and the green one will be the points we need to find the closest point among the red point. Is it okay? So we have 1, 2, 3, 4, 5, 6, 7 points of red. And we have 2 points. Need to find among these 7 red points, we find the closest points about these two. So, okay. And what is this line about? It's basically the spirit about the KD tree. So go back to here and see here. So here I say I give a very easy way to construct a KD tree is to, when we have to sort point list and then find the median points as a node, and then divide the list into 2 subtrees. And with these 3 steps, we can do it repeatedly. We can repeat this process and create a tree. And I'm gonna explain why. So let me play. I disable these confusing things. We have a bunch point, and we want to construct a tree. The way we do is, like I said here, sort point list first. So there's a lot of ways to sort the points inside C#, and you can call the link queue or something, but once we sort, the order will be like 0, 1, 2, 3, 4, 5, 6. If we sort along the x-axis, right? And we sort as an x-axis, we find a median point will be this one. And then we find the median points. We have 2 subtrees. One is the left side, one is the upside. Left side and the right side. And then we can do these 2. And when we do these 2, we sort as a y coordinate, y direction. So we need to find the median, but this time we sort it in y direction. So the median about this subtree, these 3 points, is this one. And on the left subtree, the median about the left subtree is this one. And follow this logic, we can do this one. But this one is, I think it's not that meaningful, but computer need to do things completely. So it needs this division. So we have this. If you can see each regions, for me, this one will be a subtree. This one also will be a subtree. This one also will be a tree. This one will be a tree. And all of these things will become a big tree of everything. Okay. So this example, if you see here, we have this point. Well, this one is special case. We should do here. We have this point here, and how we can use the tree structure to find the closest point. So we have this one as our roots, and then we noticed this one is in the subtree about the left node, the right node. So again, so we have this one. We find this one because after we construct the tree structure, we can starting from the node and notice this point is in the subtree about in the right subtree, and inside the right subtree is actually the right subtree beginning with this node. This point now represents a node, and this node also have a left tree and a right tree. But we notice that the point is in the right tree, and we go to a right tree. And go to a right tree means this pointer, it has a pointer to this point. So now 53, this point, is a node. And this node also have the left tree, and right tree. As we follow along, we can notice that this point and this point are a pair which owns the closest distance so far. It's a standard output about the tree structure. Okay, I see someone's nodding, and I believe we catch up. But this case is special. If we think about it together, first, this belongs to the right tree. And then we traverse in this 16, 10 points as a node. But we notice it is inside the, let's say the lower subtree. So it should be, we should go finding this point, this region, and find the points closest to this point. But in this case, the closest point about this 49 is actually only this subtree, right? Because this point is the closest point about this point. So, which means although we construct a tree, we have to somehow to make sure the calculation is smart enough that the decision we made to go to the tree and get rid of the other tree is correct enough. So this is something we have to double check. But we also have the benefit to use a tree. This is the small thing but very important in while we trying to implement KD tree. So the code here will be very simple, but to understand the logic, I think you should, if you feel confused to understand the logic, you should go back to fill this example from time to time. Okay. So I will use this one to demo the okay. Actually closest is this one. But it will go search this one. Okay. So. Oh no, this one is not correct. Okay, I see. Okay, so let's get starting to programming. I have my code posted here, and it's very simple, so I will follow along the program things, but let's say KD tree. And maybe we can do today's date and okay. you can let me open to Visual Studio and see the code here. So here we have this. Somehow I felt this is another overvalue of man. Okay. And our goal is to make this one first. We have two components and we have to make this one first. So we have one input, one output. It will be there if we do this. Input the dot point parameters. That's I'm a bit lazy, so we'll do copy cat for this, and there will be a list, right? We should access as a list. And for the output, we will have, we want to output, let's say, we want to output our main class. So it's not belong to Grasshopper classes. So it's actually, I made as my class. How do we do that? Is we add a general and this one can let us output our custom classes. So we can do we will output a 3D tree, and this one will only be one tree. So we can access that the item and output our class. Okay, and follow along. We need our class, so we can do something like here. I have already set up. Can try to do node class here, but I know for the professional, they will do something like here. But since it is not very long code, I just do it in the same document. So the node, the information about this node will be a point. Like the 3 dimension will be 3D point. And the node will have to have two nodes as the property, left and right. Although it's a node, it actually represents the beginning of the left subtree and the right subtree. Just keep in mind. And for the constructor, so maybe just say that this one is the constructor. For the constructor, we have to try to connect to our class to a Rhino word. So I'm using this constructor to make point 3D as the information we contain. So maybe you can guess I will use this constructor to put the information inside the node class. And the next, we will have a class about a 3D tree. That's about KD tree. Maybe I'll just do it the same way. 3D3. And inside we have several properties. I will explain one by one later on, but let's just do. We will have a node called root, and the root will be the topmost top node. So I just do the things here. And since the node is it's actually a pointer. So if you playing around the Grasshopper a lot, especially coding in C#, you will notice that the C# contains a lot of things as a pointer. So you have to do things. If you want to copy past one thing, you have to do like reduplicate curve or duplicate the erect or something. So it's very intuitive, especially I learned C and C++ first. So it's no pointer. It's actually pointer's idea, but it's not the pointer we can see through the code. And here is also, this one is constructor. So maybe you don't need to follow the coding things. I just want to state one by one. And here, this one is constructor, right? So as a constructor, we have two inputs, the dimension and also a list of nodes. So we have a bunch of nodes, and we put the nodes inside here, and the type is a lot of, like, we give a lot of nodes inside this make tree function and return the topmost as a node, but it actually is the root. Can everybody understand? So it will be clear though that I didn't. Maybe because since you have code, I just copy past here. Like make tree, or I use link cube to so remember to add this one to for the usage about order by. So here, if we read my code here, we have the nodes as a list of nodes to put inside a make tree function, and this function will return a node. But return this node actually it's the root about everything. It's a root about this tree. And the second parameters, input parameters, will be the depth. And if you noticed, I do this one. I say it's cases. This is a 2D case. So in 3D case, we have to. In this case, first I search this way, and I search. No. First I sort the points this way, and I sort point this way, and I sort point this way. But in 3D case, we have to sort points in 3 dimensions. So I do the things here. You can say this one is sort by x axis, and for 1 and 2 will be sort by y-axis and the z-axis. And since we want to do it repeatedly, so I do these things. Okay, maybe it's hard if we see. So the depth about a tree is the level of a tree that is different. So you can see the depth of the root is 0, and this is 1 and 2 and 3 and 4. So I believe I explained in my here. The depth of the depth definition is, first, the depth of root is 0, and the depth is the depth is the depth of parent node plus 1. So back to this one. The node of the depth of the node is 0. The depth of the B and C will be 1 and 2 and 3 and 4. And since we're doing a KD tree, in this time K equal to 3, we need to sort things every 3 times. Means we sort X axis, Y axis, and follow along the Z axis. And at the next time we want to sort, we will have to go back to X axis. So here I divide it by K, and everybody knows this one. So here K is the dimension, but in this case the dimension will be 3. We are creating a 3D tree. So this axis sense will only output 0, 1, 2. Okay, so we will do these things repeatedly, and I will do this more clearly. So this one is sort points along different axes. This big one, this part. And the second, remember we should try to tag the median node, median points was the node. See here? The second point about constructor is find the median point as the node. So the second thing I'm doing here, once we sort the nodes, I find the median, and this median will be the current node. The second step. The first step, because we have 3 directions, so I have to do this. And the second step is 1 line only. And here, the third step is dividing the list into 2 subtrees. So this is actually the third step. Divided the list into the 2 left and right subtree. So we have the left subtree and right subtree. And the tree is a bunch of nodes. So I made a list of nodes to contain the left subtree and the right subtree. And actually Google these functions. So we can do like skip, starting from the index of 0 and take the median of the nodes. So this one will be the 0 going to the half of the nodes index. So this contains the left tree. And this one contains the right tree. Now for the case, some of you might not familiar with .skip and .take. For me, it's very new stuff. So I do this quick demo. We also implement reusing a link here, and we can skip 0. We can skip 0 and take the half of the x, and we can skip from the halfway plus 1 to the end of this list, and the result is here. So the median of 0 going to 8, it will be 9 numbers, right? So the median should be 4, and the left subtree, left list, and the right list. Follow along this link function will give us this one. So you can take a look. So anyway, we're going down to the third part of constructor tree. And the next things we need to do is we need to go down one more depth. So this one is do things with kids. The fourth step we refer to this one. And until have already traversed all the points and put them on our trees. Inside our mate trees, I call them mate trees. So this function actually runs recursively. I construct a tree starting from the root. And the root, the depth will be 0. But the next time, the depth will be 1 and 2 and 3, and follow along. So by doing this recursively, we can construct a tree. So far, any problem? We have left points, left nodes, left subtree, right subtree, as a bunch of nodes. So remember, the first things we have a lot of nodes without order, but we take all the things one layer by one layer, depth by depth. The depth of 0 is fine so far, right? And going down here, 0 plus 1 equals to 1. But we have to make the left subtree. So these nodes, the left subtree of this node, we also create by this make tree function. The right subtree about this node, we also made from make tree function. So far, I believe we construct the KD tree. So you see the code is simple, but it actually take a lot of steps and solve. Yeah, I'll also copy that here. So the next step will be we need to have a function to help us find the nearest. So as this function, we'll give 1 point as our target. To you see here, you can think about as 1 point and a tree. We use this point as input, trying to find inside this tree structure which one is the closest. So we can do some graph here. If the root equals to none. Since the root, this one is global variable, I declare it here in this class. So the root is null, means there's no tree. So if there's no tree, we should return null. But if there's a tree, we should do it differently. So in this case, we didn't do the best distance, but if we want, we can output the best distance. And here's the function. So before I do, we should return the best. And the best is the type of the best is a node. So find nearest will return a node contains the best solution point. Okay. So here I have one function for finding the nearest. And this function has a definition. So I do things here. I define the nearest function as this one. And we can all look it together. So this function will compute the best point among all the points inside our tree structure and return as a node. After we get a node, we can just read what is the point it represents for. So what is important here is what is our nearest function do? So we have node, and this node will be used as representing a tree. Okay, and we have the other node, and this one will be the point, the searching point, and also the third will be index. And this index actually is much the same as the depth. So the index here is much the same as the depth before, because we have to find things in 3 directions. We search things in 3 directions. So the index here will have the same calculations like the depth here to divide it by k. And in this case, k equal to 3, because the KD tree now is the 3D tree. Okay. So what is going inside help us to find the closest point. And I'm going to explain. Like here is obvious, if it's a null, means we don't have a tree. So to prevent, if there's a no tree, we didn't have to find, there's no solution. And secondly, I have this variable named d, and d is equal to the square of the distance about the target point and the root point. So the root is an object here, right? And this object's class is a node. And inside the node, we have a property called pt to contain our point3D class in Rhino world. So I can use the benefit from Rhino command to use dot distance to calculate the distance between root point and the target point. And d actually is the square of the distance of points. Okay. And next, if the best is null, means that we haven't found the best point in these questions. We should deal with it. Or if d less than best distance, we should override d. We should override the best distance with d. Means that this is much like the if statement in our for loop, naive for loop. So we're trying to find the closest distance, right? Eventually we have to do this, but with the data structure of the tree, we can do it less times. So these things happens in for each loop in a very intuitive way from the beginning. So compare and replace. And the other special case here is if the best distance equal to 0 means it found itself. So remember I said there's a point and a tree. And this case is a point and a tree is overlap. The point actually inside the tree, they're the same thing. So this is something we are not wanted. And here, the three directions, we have a dx variable. I said initial value equal to 0. And then we calculate the distance, but it's only in one direction each time. So why I'm doing this is because we solve things in three, we solve points in 3 directions. So I can simply use the, like, this one will be the distance between root point and target point in only x direction. Does it make sense? Here. Because I only subtract in x direction. So this is in only y direction, in z direction. And after, but we have dealt things in each index case because we have 3 directions, right? We have 3 directions, so we have to tackle each by each. And this one will give us the next index. So we guarantee after 0 there will be 1, after 1 there will be 2, after 2 there will be 0 next time. And so far we run 1 time of finding the nearest. But since it's a tree structure, and the tree structure we do it recursively, while we trying to find things inside a tree. One way, although the tree can be constructed and traversed in simply while loop, but here I try to do things recursively. So this single line may be a bit difficult to read, but we can read together. So if the value of dx is bigger than 0, which means at least in one direction, the the point is, let's say, because I'm using the root point to minus the that target point, so we can thinking about, okay, do like this. If dx bigger than 0, which means root point is on the left of the target point in x direction case. Can everyone agree this sentence? Because dx is the root point minus target point. So if we add this condition in x direction case, dx will be bigger than 0's case means the root point, sorry, the right, right? What I'm trying to say is, here we have a line. This is the x-axis, and somehow we have 2 points. And the dx will be this value, right? Maybe it's not. Maybe I should do dimension. The dx will be this value. This one will be our dx. And it's bigger than, I use this x-axis to structure this x-axis and return to bigger than 0, which means this one will be the root point and this one will be our target point, right? And this way of writing is actually a lambda expression. Maybe some of you will know. Actually, this means if dx bigger than 0, then it's the left subtree about this root. And if it's not, then it's a right subtree about this root. And if you take a look about what I put in here is this expression will return either the left subtree or the right subtree about the root, right? And I put it inside this function. So this one is actually a node. And I use this node to keep going through the traverse process, going through this finding the closest process. And then my index have already at 1 to go down to the next layer. So visually, if we think it is that somehow we take step from 1 to 2, but we have to keep going down. We have to use the nearest function to keep going down. So by doing so, we have to have this at 1 index to go down to the next layer. And somehow inside the next layer, we have to determine either we should go down to the left subtree or the right subtree. So how and why, how can we determine is by this dx value? So far clear? As an input. And the target node will be the same because we eventually finding the points between the target and also the root. The target and the tree. So eventually from here, everything is over. And here one condition is if the square of the dx value is bigger than best distance, we call it a day. We make this function stop. So far, any questions?
あ、すいません。あ、すいません、日本語で。D、WT、D ですかね。D の計算式。あ、それです。これの意味をちょっともう一回説明してもらっていいですか。単純ななんかこう、二乗してるのっていうのは何か、特別な意味があるのかちょっとよくわかんなかったです。
はい。この D の意味は、結局、この D のカルキュレーションは、最後の出すのことは、距離、そのベスト距離のこと。こいつの目的は、ここです。もし、その、日本語でちょっと難しいです。英語で説明します。
はい、お願いします。英語でいいです。
So dx is either x direction, y direction, or z direction. One of these three directions, distance, right? Like I explained here. dx はこの3つの方向の中の一つだけでしょう。その dx のスクエアバリューと best distance 比べて、こいつはまずライノの中で絶対の距離でしょ。これは計算すると3D の距離。
あ、スクエアをしてる理由がちょっとわかんなかったんですよね。スクエアしないとダメ。スクエアしないとダメなのかな。なんかそこら辺の理解。
The question is like why we square distance, not directly compare the x and the distance root without square.
So since dx actually is possible to be negative.
ああ、ネガティブになる。
そうすると単純に
ああ、なるほど。
の比べて多分
So it would be okay as an absolute number.
そうですね。
Maybe?
そうするでも
こっちでもいい。ああ。理解しました。ありがとう。ね、ネガティブになるからか。OK です。ありがとうございます。
Looks like using a absolute is cheaper than using a square distance.
It really I will keep it in mind.
But I don't know if there's any other reason why you use square instead of absolute.
I think square is cheaper. It's not.
Well, since when you want to calculate the best distance, you just don't have to multiply the same distance again. So I was thinking the absolute might be cheaper. Because you don't need additional calculations.
I mean double D, right? The double D. You use
when you
distance.
calculate the best distance.
Yeah. That one, I think. So
Yeah.
you calculate twice. So I think 40,000 suggested use absurd because you don't have to calculate twice.
Yes, yes. So I believe inside this distance too, it do the square root because it's from the right triangle formula, right? So it's a squared plus b squared equals c squared inside this, and inside this one you do a square root. But here I'm just lazy to make our we can do our own distance function and without the square roots inside this one and just one simple formula.
There's also actually a function called distance2 squared.
Oh, okay.
So maybe you can replace that with that as well.
Oh, this one. So as I have to have this square root to do especially this one. Sorry, I do things messy. But in my mind is something like this.
Right.
Yeah. So anyway, but good question. I think I haven't explained to this point here. But this one is guaranteed that we should have an endpoint about this recursive things, right? We should stop this recursive once this condition fixed. Like we meet these conditions and then we stop our calculation, right? Okay. So here is normally we'll close this lesson, but if you remind the explanation here, this point is special. In this case, we have to do it certainly. We have to tackle this problem certainly. And the way we're doing this is we once again to come to see if dx is bigger than 0. But in this case, we also to evaluate the right node and the left node. So in this case, in this point, we will first go to a right subtree and then go to this subtree. Go to this subtree. Since this one belongs to this subtree, but it's not good. It's not correct. We should also check this subtree for this case. So as a result, we have to do these things here, left to right, right to left, and the other things is the same. So I will give a demo about if we have this one or without this one. Let's just say if we comment out this one. Yeah, maybe I just go back to this one. This is from my GitHub page, and we can find this one. Because maybe you know these GUID things, I just want to make sure that I can have two things which are the same. So I use the previous. So if I comment out this one, in this case, you will find the wrong point, right? But in the normal case, in this point case, it will work perfectly. So I want to demo this by actually build this one. Okay, so we can make this one. We put here, and go to my maybe I need to I made a new line. And our GHA will be this one, and this base. So here, when we open up the where is it? And here, and fine. We have KD tree and as the output. Now we should tackle this. We should take this point. This one is normal case. So it returns to the correct solution. It's work perfectly. But if we use this point, we find this one, right? It's actually the closest is this one, right? This is 2, because this is 2 plus 1. It's 2 squared plus 1 squared. This is a slide. So this one will be perfect. Perfect action for this case. But it didn't. Because I comment out the list line. So if we do the process again, then maybe there's a better process while I do this. But this really again, I build it again and try to find inside my try to find this one. Okay. This one is the nearest. And we do okay. Let's see. Yeah. So the point now is correct, right? This one. From the list one, we search to the correct answer. The previous one is searched to this one. It's not correct. For the normal case, it works perfectly to find the correct one. So we can guarantee our algorithm work in a very simple cases with like 7 points. Then we can do a bunch of points and actually have the power of binary search tree, KD tree. So maybe we can quickly run through what is inside this component. But the algorithm is just the algorithm. No, I just put it to the other file. So we have this component, right? And in this component we have these classes, but we have this component as well. The file nearest inside my solution file is this component. And this component have two inputs. One is KD tree, and this one is my own classes. And this one is simple points 3D. And the output is the closest point. And how we construct this is to have two classes and add genetic parameter. As for this one is for taking out KD tree, custom classes. And the other is simple, is a point. Point will be a point, not point. Anyway, so this simple point and finding this item and return the closest item. And this no other close here, so this one is simply for like this object-oriented feeling about, oh, I have built this one first, and while I'm searching, I'm separated here. If you want, you can go inside one component. I just think we can compare the KD tree and also the launchpad tree together. So here, once we have KD tree and it's starting from nothing, and we take the KD tree as a reference inside, and now we have a tree, and we can do it like something like here, and this. Now I know this one can also be doing like this, and to okay, so maybe here, and we take the target point, and we use the phi nearest, and remember the phi nearest, we define it inside here, the phi nearest. And the important thing about the phi nearest, we have this function, it's called nearest. And the nearest is a function do things recursively. And we also have this for special cases. Yeah. And that's all. And we return, since it's the nearest node, the nodes point. So back to the right node's world. Okay, so far. That's how I construct this too. And for today's purpose about introducing this tree is actually for the other file contents in my GitHub. And this one has a lot of points, so makes it very shockingly slow. I'm trying to do things here. Now we know this one is very slow because it runs not if for good n times. And I think this 4 takes log n time. And this one is our today's target. Okay. We're starting from simple like 1,000 points. And okay, we can do something like this. 5,000 points and split it into this A and this B, and this one will be 1,000 as well. So, oh, this one is for the target point. Okay. For 1 point. We're starting from 1 point. Okay. And then compare starting from, we should see, yeah, although I disable everything, it still preview the point. Okay. This one should enable. And maybe this one should disable. So when you open my file, please be careful because it's very huge. And let's do 1,000 points. I don't have 1,000. Okay, let's do 1,000. This 1,000 points. And we take this. Okay. And I don't know if you had a Meta Hopper or not, because I recently know Meta Hopper had this launch bottleneck navigator. This one will find it the one costs you most time to calculate. So since right now all the calculation things happen in this one, so we will find in this one, and we should first know the point. One point, this one. And you found the closest point without any problem. And this is very small number. We can compare this too. You see, this is a naive for loop. We just travel through all of the distance and suddenly it gets huge. It takes almost 200 times about this closest point component. So this is not something we want, and it will definitely crash your computer after we increase this number. So we should see something nice. Oh, but anyway, we can compare. I hope we can compare this one. So I do the points 3D, but somehow it's not that quick. I should recompute. The second time it goes down very quickly, but the original closest point is still faster, 5 times faster. But inside this point 3D dot close points, we have near this point, and I call this function closest point in the list is a default function, and return a nearest point. But it's still fast compared to this one, right? We should recompute. Where's my? Okay. It's not obvious, but slightly faster. Well, once we go, we should take this time to see recompute. Create R3 takes 1 millisecond, and finding is super fast. It's going down like here. And ours. So this one, okay, it will show right in the middle of the canvas. So my way of construct KD tree is huge. It's slower in the case of 1,000 points, even slower than we do a naive way. And R3 is tackle this problem very good. But somehow I do second times is, you see my KD tree is going down here. So somehow maybe there's something about the coding machine level, but I don't know. But this seems very unimportant. It's not a big deal because we didn't have that really big number of points. But once we go to this one is 10 times larger than this one, right? It's 10,000. So you see my KD tree. You combine my KD tree and find nearest. It still perform well. It's still slightly better than this one. This one is 2 times of the number we found it. And actually, while we doing is increase the tree, the point inside tree, we can increase the point about searching. So let's say now it's not 1 point to a tree. There will be 1,000 to a tree. I'm not sure if it will correct. This one should definitely. I would do like 100 first. Okay, oh, fine. But this one, my KD tree and the R tree. R3. This one. Doing some. So this going down. And didn't get better after I recompute. So this one is not good in case of we increase the searching point. So it's not, I think it's not wise if we still keep compare the current state with this component. So this component. And this one working red might be the next one will break up. Still white, but I should enable. Okay, so we added 5,000 more points here. This one become the slowest one, and also we can go for maybe we compute. Yeah. So see if we compare to R32, this 2 is create R3. R3 closes. This 2 is 64 milliseconds, and the KD3 is like for 130 milliseconds. Still, R3 is slightly faster, but we didn't crack out why if this part work test. Okay, it will be all of today's lesson, I think. So while you do, maybe because I have to tackle this crackdown issue every day, so some tips like solution, disable solver will guarantee. And what I always doing while doing large points, I know that it's very heavy if we want to preview them. So I uncheck the preview, but I still need the data behind. Okay, so it's all about today's lesson. Thank you very much.
It was very interesting one and very informative. Thank you very much, Jim. So and now I think all of us know each other, so maybe the Q&A time. Anybody have a question for this session? We can ask it over. I have actually one question. In the nearest function you implemented, you have both nearest one when you search left and right node, right? You explain, yeah, for the special cases, you have that you also search for right instead of only left. But is that way is calculating that means calculating both? What or sorry, I didn't understand that the part. For the nearest dx 0 is bigger than 0, you have you search left.
So this one?
Yeah, that one. So the nearest one, you search first left, and then you also search right, right? So you have both. You search in the both. Is that means or I'm sorry. I think I couldn't. I couldn't ask him well, but 両方、sorry, in Japanese 両方サーチしてることにならないのかなっていう。ここでリターンできるから、リターンできなかったときに、ライトもサーチしてるっていうことか。からいいのか。
このことですか？
For the special cases?
This one?
For this, yeah, for the special cases.
It's
If you cannot return, you have a special case. Is that correct? Or you have to also always have to search in light node.
yeah, and this case is
Yeah, this case is for the special case.
yes.
You
And
have to search for the special case, or you have returned it, so that it's okay for both. So you have search in left and right in this code, right?
I see. So I believe the behavior will be differently if you put
Okay.
This one might be heavy or a lot of heavier than you put this line. Yeah. Because normally you traverse to the tree, you use this one.
Yeah, okay.
And even before you check, you find the solution. You are still going down to the tree. So what I'm trying to say is, in this case, you have to at least find a solution. Then we will try to maybe I can explain this. So I didn't have any software to help illustrate this one, and I always do this. Screenshot things. Okay. For example, we always starting from root. And let's say this is the correct answer. This one is correct. This one is correct answer.
Okay.
But since we're going down one by one, no, it's actually not like this. We're going down one by one. But what if in this case, suddenly we found, oh, the point is more likely in the left subtree, you will find the correct one. But actually the correct one is this one, right? So in this case, we guarantee we have a solution, but it's not the correct solution, right?
Okay.
So in the this node to the this node, this actually implement one kind of the nearest function, right? But this nearest function from the solution, it returns this end. This was end. So this end means we give this one solution as our nearest point, but it's not wanted. But with this, so we go back to, you see, this nearest function, while you return nothing, you will go back to this one. This point, you keep going to this special case to traverse to this point, to find this point. So let's say the different example, like you get wrong very quickly. Let's say eventually we found this one. We found this one as a solution, but the correct one is this one. So after we found the, it returns null, it returns nothing, you go back to here. And if it returns nothing, you go back to here. But starting from this layer, you will go down to find the correct one. Because I do like this. But if we, in the normal case, didn't go wrong, we'll go down, and return nothing, return nothing, return nothing, and return nothing. And usually, you will something be like this. So that's what I say. If I put this one right before this one, will hardly influence the speed, because this one actually means.
Yeah. Okay. Searching for both tree. Yeah. Okay.
So this is important things need to guarantee how you traverse back to.
I see. Thank you very much for the explanation. It became clear. Thank you so much.
Okay. This is very abstract.
Yeah.
Me as well.
ありがとうございます。じゃあ、一応一人一人